Hello, I am Steve Halliday, a doctoral student working with Dr. Jerry Dozier at Auburn University. In this paper, entitled A Comparison of Genetic and Swarm Intelligence-Based Feature Selection Algorithms for Author Identification, we are working in the field of author identification, specifically in the area of feature selection. As researchers broaden the features they consider for author identification, the number of features can become a problem both in terms of accuracy and computational horsepower. Therefore, selecting the appropriate set of features becomes an important aspect of author identification. In this paper, we use three classes of features and consider genetic search and swarm intelligence algorithms to perform feature selection. Swarm intelligence algorithms are optimizing machine learning algorithms based on emergent, self-organizing behaviors often rooted in behaviors found in nature. These swarm intelligence algorithms use collections of entities where the entities pursue an individual course and interact peripherally with other entities in the swarm. The benefit of both genetic search and swarm intelligent algorithmic optimization approaches is that they find very good solutions to problems that defeat traditional search approaches. Author identification systems extract characteristics from text as features and use those features to try to identify the author of the text. Initial author identification systems relied on primitive word frequencies, but more recent advancements employ other text attributes such as topic modeling and sentiment analysis. Researchers are increasing the number and types of features they consider in an effort to improve identification systems. However, as we include more and more features, the computational costs increase, and it's not always clear if these features add significant value. Therefore, it is valuable to find mechanisms that identify the useful features. This process of identifying useful features becomes an optimization process to which we can apply genetic search and swarm intelligence algorithms. In this paper, we have compared one genetic search algorithm and four swarm intelligence algorithms. The genetic search algorithm is GFAS, which is an acronym for Genetic and Evolutionary Feature Selection, based on previous work by Gaston et al. The four swarm intelligence algorithms include particle swarm optimization, artificial bee colony optimization, ant system optimization, and glowworm swarm optimization. Gaston et al.'s GFAS system is a steady-state genetic algorithm that uses genetic crossover and mutation to explore the search space. Particle swarm optimization also uses feature masks to represent individuals in the swarm. The swarm then moves through the search space, much like a school of fish or flock of birds. The members of the swarm start at random locations within the search space and start moving with random velocity. At each iteration, members of the swarm update their position based on the previous position and velocity. Then, individuals update their velocity based on the best position they have seen so far as well as the best position as seen in the entire swarm. Since each particle needs to evaluate its position on each iteration, the total number of evaluations is the product of the swarm size and the number of iterations. Artificial bee colony simulates a hive of bees searching for nectar. The bee population is divided into two sets of bees, worker bees and onlooker bees. Again, the feature mask represents the location of the bees within the search space. Worker bees evaluate their position and return and report their results to onlooker bees. Onlooker bees select a worker bee to follow based on a fitness probability function and follow the worker bees back to the general vicinity where the worker bee was. The bees keep track of their fitness values, and if they are unable to find better fitness values within the vicinity, they abandon the location and choose a new location at random. Since bees never return to the exact same location, the number of evaluations performed by this algorithm is a product of the population size and the number of foraging iterations. Unlike other swarm intelligence algorithms, ant system optimization is a reinforcement algorithm. For ant system swarm optimization, the feature mask represents the path ants take to try to find food sources. As the ants travel the path, they lay down pheromones. Better paths have higher concentrations of pheromones, which attracts the attention of more ants. The ants make small deviations along the path, which facilitates exploration. Most useful paths emerge as representations of the most effective feature masks. The number of evaluations performed by ant system optimization is a product of the number of iterations and the number of paths considered on each iteration. Glowworm swarm optimization is a lot like particle swarm optimization, where other individuals in the population affect the velocity of the particle based on how near and how fit the neighbor is. Since each individual assumes a new position on each iteration, the total number of evaluations is a product of the population size and the number of iterations. In addition to the 5 algorithms I have just described, as a baseline we also use an algorithm that merely generated random feature masks. Following the work of Gaston et al., we used 93 features from linguistic inquiry and word count, 176 sentiment analysis features, and 45 topic modeling features for a total of 314 features. We pre-processed each set of features using TF-IDF standardization and normalization. Then we concatenated the 3 feature sets together into one feature set. We used a subset of the Casus 1000 dataset. The Casus 1000 dataset consists of a set of blog posts of 1,000 authors, with 4 samples for each author, for a total of 4,000 labeled samples. We used stratified 4-fold cross-validation so that we trained on 3 samples per author and tested on the 4th sample and performed this training testing 4 times. We used the 6 algorithms previously described to generate feature masks, which we evaluated with 3 different author identification systems. The 3 identification algorithms we used included linear support vector machines, radial basis function, and multi-level perceptron. The fitness function we used is the accuracy minus a weighted ratio of the number of features. This allowed us to influence the importance of minimizing features. Note that a feature weight of 0 is a fitness function based completely on accuracy. We trained using this fitness function, but reported results based on accuracy. We considered feature weights of 0.0, 0.1, 0.3, 0.5, and 0.7, 0.9, and 1.0. We ran all combinations of 6 feature selection algorithms with 3 identification algorithms for each of the 7 feature weights. In each case, we allowed the feature selection algorithms 15,000 feature mask evaluations. We also made 30 observations for each of these combinations, or in other words, we ran each combination 30 times. I will now present the results of the experiment using one table for each of the 6 algorithms. Each table shows results for each of the 3 author identification algorithms in a separate section. In the first table, we see the results for the artificial bee colony optimization algorithm. Let me just take a moment to explain the layout of these tables using the artificial bee colony optimization table as an example. We see that the table contains 3 major horizontal sections, one for each of the 3 identification algorithms. We also see 4 columns, where the first column, labeled hybrid, identifies the 3 major identification algorithms. The second column, omega, is the feature weight used in the fitness function. The third column is the accuracy achieved by the combination of feature selection algorithm and author identification algorithm and the feature weight. The fourth column shows the percentage of the 314 features used. Note that this percentage of features used is not the overall fewest features used, but corresponds to the observation in the third column. The third and fourth columns have pairs of numbers. The first number in the pair is the best of the 30 observations. The second number, in parentheses, is the mean of the 30 observations. For each of the author identification algorithms, we have highlighted the best observations in bold. For accuracy, this is the highest best observation, and for feature reduction, it is the lowest observation. Note that since the percentage of features used corresponds to the observation in the third column, the best feature percentage might be higher than the mean feature percentage. As we go through these tables, you will notice that the best accuracy observations all fall within the range of 96 to 100%, except for the random algorithm, which is 82 to 87%, much lower as would be expected. In this table showing the results of the artificial bee colony optimization, we see accuracy values of 98, 97, and 96% for the LSVM, RBF, and MLP identification algorithms respectively. We also see that we are using less than half the features, 46.5% for LSVM and about 44.25% for RBF and MLP. The next table shows the results for the ant system optimization. Notice that this table shows comparable or slightly better accuracy than the artificial bee colony optimization algorithm, but slightly fewer features than the artificial bee colony optimization. The third table shows results for glowworm swarm optimization feature selection that is roughly comparable to artificial bee colony optimization. That is, accuracies range from 99 to 96%, and feature reduction percentages are in the mid to low 40% range. The fourth table shows results of particle swarm optimization feature selection. Here we see accuracy comparable to ant system optimization and feature reduction slightly better than artificial bee optimization. The fifth table shows the results of random feature selection. As we would expect, its accuracy is much worse, in the mid 80%, and its feature reduction is in the lower 40% range. The sixth and last of these tables shows the GFAS algorithm, which pegs accuracy and demonstrates significant reduction in the number of features, that is, down around 13 to 15% of the features. We performed an ANOVA ranking analysis of the feature selection algorithms for each of the author identification algorithms and for all the feature weight values. We did this by first performing an ANOVA ranking for each of the feature selection algorithms to find the best equivalence class for each algorithm. Then we combined these top equivalence classes and performed a combined ANOVA ranking analysis. This two-pass approach explains why not all feature reduction weighting values appear for all algorithms in the final ANOVA rankings. This table shows the resulting equivalence classes from the analysis. The first column lists the identification algorithm. The second column shows the equivalence class ranking for each of the identification algorithms, and the third column shows the feature selection algorithm and the feature weight combinations for each equivalence class. We might note in this table that GFAS always ranks in the top equivalence classes, and ant system optimization comes in second. The rest of the algorithms trail, with the random algorithm always in the lowest ranked class, as might be expected. Given these consistency rankings, we took the top ranked equivalence classes for each of the identification algorithms and plotted the feature consistency, or in other words, how often the feature appeared in the resulting feature set. We have three charts to represent the feature consistency, one for each identification algorithm. In each of these charts, we plotted the 314 features along the vertical axis and the frequency ratio along the horizontal axis. You may recall that the feature set is a combination of three different text characteristics, namely linguistic inquiry and word count, sentiment analysis, and topic modeling. We have color-coded the bars to indicate which of these features belong to which category. The first chart shows the consistency of the top equivalence class for the LSVM identification algorithm. The second chart shows consistency for the top equivalence class for the RBF identification algorithm. And the third chart shows the consistency of the top equivalence class for the MLP identification algorithm. All three charts look very similar. The bar color coding makes it apparent that topic modeling played a significant role. This is understandable and likely because the data consists of blog posts, where bloggers generally blog on specific topics, so the topic correlates strongly with the author. Here are a few key takeaways from this study. One might incorrectly anticipate that optimizing purely for accuracy, in other words, omega equals 0, would yield the best observed accuracy across all feature weights, but surprisingly, this is seldom the case. Instead, we see a general trend where best accuracy is achieved when omega is between 0.1 and 0.9. This attests to the benefits of feature reduction beyond computational advantages. On the other hand, when omega equals 1.0, which increases the bias towards feature reduction, intuitively we see a diminished accuracy. Also, it is interesting to note that GFAS was very successful at significantly reducing the number of features while still maintaining high accuracy across all author identification algorithm configurations. Ant system optimization was moderately successful at reducing the number of features, whereas with the other four algorithms, one can observe there is some influence of the feature weight on the number of features, but not nearly to the extent of GFAS or Ant system optimization. We see that all four swarm intelligence algorithms allowed the author identification system to achieve excellent accuracy, but we also see that the genetic algorithm not only achieved the best accuracy, but also significantly reduced the number of features.